Welcome to the deep dive. Today we're tackling a really fundamental question. It's about how we actually know what's true in science.
Right. How researchers go from just being curious to getting, a solid answer.
Exactly. So we're diving deep into study designs. It sounds maybe a bit technical, but it's the hidden architecture behind, well, everything you read about discoveries or health claims.
Hmm.
Our mission is to decode these plans. Researchers use how they gather data, analyze it, and why picking the right design is so crucial.
It absolutely is. Study designs are, they're really the bedrock, the blueprint for any kind of solid research.
The blueprint, okay.
Think of it as the core methodology. Without a good design, you can't be sure your findings are accurate or, reliable.
Right, that someone else could repeat it.
Precisely. And it has to align with your research question. Critically, it determines how strong your evidence actually is.
And for our listeners.
Well, understanding these designs gives you a kind of superpower. You can actually evaluate the research you come across, headlines, health trends, whatever.
Okay, let's unpack this then. If someone's totally new to this idea, how would you describe a study design, more than just a plan?
Yeah, it's definitely more than just a plan. It's a structured methodology. It outlines exactly how you're going to collect data, analyze it, interpret it.
To answer that specific question.
Exactly. And its importance, well, first, validity and reliability, making sure your results are accurate and repeatable.
Okay.
Second, alignment, keeping you focused on the original question. Third, strength of evidence, like we said, how convincing are your findings?
Right.
And finally, it helps meet, all the requirements for publication and regulations. It's the whole scaffold.
The framework, got it.
Yeah.
And generally when we talk designs, there are two big categories, right? Observational and experimental.
Precisely. Those are the main branches. In observational designs, researchers are essentially, well, watching and learning.
Just observing.
Yeah. They look at associations between, say, an exposure, like a habit or something in the environment, and an outcome, maybe a health condition,
Yeah.
but they don't step in or change anything.
Okay. And within observational, there are different types. Let's start with descriptive studies. I think of these as just focusing on the what, like taking a snapshot while standing still. You just describe what you see right there, not why it's happening. What's their value?
That's a perfect analogy. Descriptive studies are mainly about understanding patterns, disease patterns, behaviors, conditions in a population.
So generating ideas.
Exactly. Their main value is often hypothesis generation. They're great for spotting new diseases, rare conditions, things like that.
Like a case report.
Right. A case report details one unique instance, or a case series describes several similar ones.
And they're useful because.
Well, they're quick, pretty simple, cost-effective, good for that initial hypothesis stage and for public health planning.
But the big limitation.
The big one. They can only describe what is happening. They can't tell you why. No cause and effect determination.
Okay.
Like Leon Gordas said, they're the necessary first step to understanding a problem, just getting the initial picture.
Right, the first sketch. Okay, so that's descriptive. What if you want to see if things are linked, even from afar? That sounds like correlational studies, maybe looking at whole groups.
Exactly. You mentioned the hot air balloon analogy earlier.
Yeah, observing different islands, different populations, from a distance, no interaction.
That fits well. Correlational studies, or sometimes ecological studies, look at relationships between variables at a group level.
Like comparing average ice cream sales and crime rates across different cities.
Precisely. Their strengths are they're quick, cheap, good for generating more hypotheses, and can show broad trends.
But the same limitation again.
Same key limitation. They show association, not causation. Just because two things trend together at a population level doesn't mean one causes the other.
Right, the summer heat example causing both ice cream fails and maybe more people being out, leading to more crime. Not the ice cream causing crime.
Exactly. So you see a link, but you have to ask, is it causal or just happening together? That's the critical thinking part for you, the listener.
Okay, that makes sense. Which leads us naturally to analytical studies. These try to get more into the why or how, right, examining the association more closely.
Yes, exactly. Analytical studies aim to bridge that gap from just observing patterns to understanding potential causes. Like Noel S. Weiss said, they transform patterns into potential causes.
So, digging deeper.
Right. One common type here is the cross-sectional study. This is that snapshot design again, but often with an analytical angle.
How so?
You collect data on both the exposure and the outcome at the exact same time.
Like that survey example. 10,000 adults check their blood pressure and BMI right now.
Perfect example. It measures prevalence, how common something is right now, and looks for associations. Strengths are it's quick, cost-effective, generates hypotheses, calculates prevalence, and you can look at multiple things at once.
But the catch.
Still can't definitively prove cause and effect. And the big issue is temporal ambiguity.
Temporal ambiguity.
Yeah.
Meaning you don't know which came first.
Exactly. Did the high BMI come before the high blood pressure or the other way around?
Oh,
Or did something else cause both? The snapshot doesn't tell you the sequence.
Okay, the sequence matters. Got it.
Yeah,
What's next in analytical? Case control studies. You said these are retrospective.
that's right. Retrospective. Here, you start with people who already have the outcome, the cases.
Like lung cancer patients.
Yes. And you compare them to a similar group without the outcome, the controls.
Healthy individuals, maybe.
Right. And then you look backward. You investigate their past exposures.
So asking the lung cancer patients and the controls about their smoking history.
Exactly. The goal is to look backward to assess previous exposures. It's very clever and efficient, especially for rare diseases.
Why rare diseases specifically?
Because if a disease is rare, waiting for enough people to develop it in a forward-looking study could take forever. With case control, you find the cases that already exist and work back.
Okay. Efficient. Downsides.
The main one is recall bias. People might not accurately remember past exposures, or their current illness might affect their memory of the past.
Makes sense. Hard to remember details from years ago.
Yeah. And another thing, they can't measure incidence, the rate of new cases. You're only looking at existing ones.
Got it. So case control looks back. What about looking forward? That sounds like cohort studies.
Exactly. Cohort studies are typically forward-looking, though they can sometimes use past records retrospectively. But the classic approach is perspective.
Meaning?
You start with groups based on their exposure status. One group exposed to a risk factor like smoking.
And a comparison group not exposed, non-smokers.
Right, and then you follow both groups over time.
To see who develops the outcome, like lung cancer.
But precisely. The goal is to look forward to report development of outcomes.
And the big advantage here.
Establishing that temporal relationship, you know the exposure came before the outcome, which is key for suggesting causation.
So it helps with that chicken and egg problem.
It does. You can also calculate the rate of new cases. They're good for rare exposures, and you can study multiple outcomes from one exposure.
Sounds powerful. What are the drawbacks?
Well, they can be very time-consuming and expensive, especially if you follow people for years or decades.
I can imagine.
And you can lose people along the way lost to follow-up, which can bias your results. Or there might be selection bias if the groups weren't quite comparable to start with.
So, strong evidence, but resource-intensive and potential pitfalls.
That sums it up well, watching the story unfold from exposure to outcome.
Okay, that's a great tour of observational studies, watching and analyzing patterns. But if you really want to nail down cause and effect, that brings us to experimental designs, the gold standard, right?
Absolutely, the gold standard for causation. As Kenneth Rothman put it, they offer the clearest lens for seeing how an intervention leads to an outcome. It's about actively testing.
And the king of experimental designs is the randomized controlled trial, RCT.
That's the one. RCTs are fundamentally interventional. You're not just observing, you're doing something to evaluate an intervention.
Like testing a new drug.
Exactly. Or a new teaching method, a therapy program, anything like that. The power comes from 3 core elements: randomization, blinding, and a control group.
Okay, break those down. Randomization. You had that great analogy. The spinning wheel.
Ah, yes, the spinning wheel. Imagine using it to randomly assign participants to different groups. Say, one gets the new drug, the other gets a placebo or standard treatment.
And why is random assignment so important?
Because it makes the groups as similar as possible at the start in terms of both things we know about and, crucially, things we don't know about. It minimizes bias. Any difference in outcome is then more likely due to the intervention itself.
Okay, so randomization creates comparable groups. What about the different doors and the wizard researcher?
Right. The different doors represent the different interventions each group receives. And the wizard researcher, that's the blinding part.
Blinding meaning?
Often, neither the participants nor the researchers assessing the outcomes know who is in which group, the intervention or control group. This prevents conscious or unconscious bias from influencing the results.
So the researcher observing doesn't have expectations based on who got the real drug.
Exactly. And having that control group gives you a baseline to compare against. It's this combination of randomization, blinding, and control that provides such strong evidence for cause and effect.
Makes sense why it's the gold standard. Are there other experimental types?
Yes. We also have quasi-experimental studies. These also involve an intervention.
So researchers are still testing something.
Right, but the key difference is there's no randomization.
Ah. So maybe comparing outcomes in a school that implemented a new program versus a similar school that didn't. You can't randomly assign schools.
Precisely. You're using existing groups, so they might not be perfectly comparable from the start, which makes the evidence less strong than an RCT, but still valuable.
Okay. And you also mentioned animal studies.
Yes, briefly. These are obviously experimental, often used early in research.
Or what kinds of things?
Understanding basic disease mechanisms, pathophysiology. Testing drug safety before human trials. Exploring genetic manipulations in a controlled way. They're a vital early step.
Wow. Okay. So quite a range of designs, each with its own strengths and weaknesses. This has been incredibly clear.